In this video, I'm just going to go over some of the key ideas for deformation of solids, looking at those questions we posted on the classroom a few days ago. Taking this question here, first of all, and some people get confused about the elastic limit. Common misconception is that that is where the limit of proportionality is. They are separate things. So on a stress strain or a force extension graph, this could be force and extension, you get a straight line from the origin. This is the part that obeys Hooke's law. This is Hooke's law here, where F is proportional to X. When you get to the end of that point, the limit of proportionality, it starts to curve. So you can always see it on the graph because it starts to curve. And that is not the same place as the elastic limit. We can only find the elastic limit by experiment. We do that by adding masses, continuously increasing the force until we take it off after each one, until it no longer returns to its original shape. So where's the elastic limit? Well, it's definitely not at A, because this part is where it obeys Hooke's law. It always tends to be after it starts to curve. We can see that C, when we remove the stress or remove the force at C, it does return down here, and there's a clear deformation. It's not returning to its original length. Remember, strain is extension over length. There is some strain. That means there is some extension left. So it can't be C. D is just crazy down there. I don't know what that's doing. So that just leaves B as our only option for the elastic limit. And just another idea coming from this graph, remember the gradient of a stress strain graph is the Young modulus, which is symbol E. That's the gradient. And remember, the Young's modulus just depends on the material. So it doesn't matter how much copper you have and what you do to it, this Young modulus stays constant. Plastic deformation, one of those key ideas you need to be able to define. Plastic deformation always obeys Hooke's law? No, it doesn't. After that point, it's normally where it's curved. It doesn't return to its original length. It does not return to its original length when the extended force is removed. Well, that's the answer there straight away. So remember, plastic deformation, you remove the force. The only way to find it is by experiment. Reduce the force and see if it returns to its original length. If it's an elastic deformation, then it's going to be this one. It will return to its original length after the force is removed. So we can only find that by experiment. That's one of the definitions you need to know for this topic. Other key ones, remember the definition of stress, strain, and Young's modulus. You need to make sure you know all those definitions really well. So remember, stress is force per cross-sectional area, or per unit cross-sectional area, and strain is extension over original length. Common mistake is people forget to say cross-sectional area, they just say area. That's not correct. Young's modulus is defined as stress per unit strain, or stress over strain. One of the final ideas that people get confused with is elastic potential or strain energy, all work done. They're all related. On a force extension graph, the area under the graph is equal to the work done, which is equal to the elastic potential energy or strain energy gained. Why? Well, work done is force times distance moved. Well, the area under the graph is timesing the two axes together, so it's force times extension. Extension is just the distance moved, so that's why it's work done. So a question like this, it asks what's the best estimate of the work done? Well, it's the area under this graph, this area here. This is a curve, so unless we integrate, we don't know exactly, but we can approximate it as a triangle and find the area. Half times the height, which is the force, times the base. But make sure we get that into meters. It often won't be, so we need to convert it to meters first. So that'll be 50 times 2, which is 100. 100 times 10 to the minus 3. So it's going to be 0.1 joules. Now you might be thinking, well, it's that, but actually remember we haven't taken into account this little bit above. So it's definitely not that, and it's definitely not that. Could it be 0.2? Well, 0.2 would actually have to be the area under this of this whole rectangle, so it's definitely not that big. It's a little bit bigger, so your answer is C. And the next topic that was raised as one that was hard are springs in series and parallel. What we mean by that is springs which are arranged in series, so in a row like this, or next to each other in parallel. So in this question asks you to find the overall spring combination which has an overall spring constant. Remember, spring constant is K of 8. The equation is F equals Kx. So how do we find the spring constants of the combinations? Well, we just need the total force divided by the extension. So for this one, the total force is 1.6. Oh, and remember that is through both these springs. The extension, total extension, is 0.4. So we can then work out what the spring constant is there. Now, careful when they're in parallel, just remember the force will be halved, so each one will take 0.6 newtons in this case. So we want to find the spring, but if we want to find the overall spring constant, we're going to take total force divided by the total extension. I'm not adding the extensions together because if you think about it, they're both extending in parallel, so you're going to go down by that amount. You continue to do that till you get the answer. So just be careful when they're in parallel. Remember the force would be shared between them if you're looking at it from that point of view. But when they're in series, the force acts on both of them by that amount. So we can find another example here. So this spring arrangement here, spring P and Q are identical and each have a spring constant of K. So I'll label my diagram first. Spring R has a spring constant of 3K. What is the increase in the overall length? Well, the way we can do that is see how much this spring extends by and one of these springs extend by, because they'll both extend by the same amount, and then parallel, so they'll only go down by that amount. Let's start with this one. F equals kx, and we want to find the increase in length, that's the extension, that's x, is equal to F over k. Force is W. There's no numbers here, so we're going to have to do it in terms of algebra, but that's fine because all the answers are like that. So this will be W over 3k will be the extension of spring R. So we've got one extension here. Let's now do the top part. Same thing, x equals F over k. Now the force is W here. That's going to act down on here, and each of these are going to take half of that. So it's going to be half or 0.5 W divided by k, which is just k. That can be written as W over 2k. So these two here are the two extensions. We just need to add them together now to find the total. So I'll do that over here, W over 3k plus W over 2k. Easy way to do this is probably find a common denominator, which is 6k, and then we'll have to times the top by 2w there, and 3w. So you can see that we end up with 5w over 6k. So there's our answer. So a bit of a tricky one there because there's no numbers. If you'd rather, you could give the numbers. You could just say W is 1 Newton and K is 1, and therefore you could use it doing numbers and see which one gives you the right answer.